we do the example right in front of this? Not completely, no. We did example 10A, I think, but not 10B or C. Let's look at 10B, see if we can make sense of this. For each of these, the points where they are continuous are going to be exactly where they are exactly points in their domains, and the points where they have discontinuities, I want to say in these cases they're likely to be vertical asymptotes, but let's see if we can confirm that or maybe find an exception to that. It wasn't a vertical asymptote at x equals 7 for this one. That was the one point of discontinuity. In the B part, if we factor, I think a vertical asymptote, but maybe something else. How does this work out? Is that it? X plus 4 times x minus 3 in the numerator, x plus 4 times x minus 5 in the denominator. Now, the x plus 4s would divide out if we were going to evaluate this function anywhere but -4, or if we were going to evaluate the limit. We'd divide those out. However, we do have to acknowledge that the function is undefined at -4, because -4 makes the numerator 0. It also makes the denominator 0. So it'll be undefined there. When evaluating the limit of g of x as x approaches -4, because we can divide out the x plus 4s, we can actually evaluate the limit as x approaches -4 of x minus 3 over x minus 5, and it exists and equals whatever -4 minus 3 over -4 minus 5 is, evidently -7 over -9. Okay, so the point -4 7/9 is a hole in the graph. That is the point that the graph is getting really close to. When x gets really close to -4, it's just that x doesn't actually get to -4, so that point is not on the graph. It's a point of discontinuity, and it's a removable discontinuity. If we wanted to remove this discontinuity, we could do so simply by defining the function to equal 7/9 at -4. We could do something like this. We could say g of x equals x squared plus x minus 12 over x squared minus x minus 20 if x is not -4 and equals, let's see, 7/9 if x does equal -4. And that would fill in the hole, and it would remove the discontinuity. Now, as it stands, it's just an empty space. The way the function is current, we might want to change its name when we actually define it there. But as it stands, there's just an empty space there. So G has a removable discontinuity at x equals -4. What is the other discontinuity? Where is it? X equals 5. And at x equals 5, we'll talk more about infinite limits in the section 2.5. But as x gets close to -5, we could also use, positive 5. To positive 5, we can also use this expression. But in fact, it's really close to positive 5. The denominator gets really close to 0. The numerator is close to 2, but the denominator is close to 0. So we take a number this close to 2 and divide it by a tiny, either positive or negative, depending on which side of 5 x is on. It's either going to be a great big positive number or a great big negative number. So it's going off to positive infinity or negative infinity as x gets really close to 5. So G has a vertical asymptote at x equals 5. The vertical line, x equals 5, is vertical asymptote. So two discontinuities corresponding to the two numbers that fail to be in the domain, and those are the two different behaviors the function exhibits at those numbers. What's going on with C? Our concerns are these. We have to take the square root of x plus 1. So x plus 1 better be greater than or equal to 0. We have to divide by whatever 3 minus the square root of x plus 1 is. So 3 minus the square root of x plus 1 better not be 0 itself. And we have to take the square root of 100 minus x squared. So 100 minus x squared better be greater than or equal to 0. So if all three are satisfied, then x will be in the domain. And otherwise, there might be a point of discontinuity inside there somewhere. So certainly x would need to be greater than or equal to -1. And what can we say here? Negative square root of x plus 1 better not be -3. The square root of x plus 1 better not be +3. What can you take the square root of and get +3? 9. So x better not be the number you can add 1 to and get 9. Right? 8. X plus 1 better not be 9, so x better not be 8. So there's an issue with x equals 8. We want to explore how the graph may fail to be continuous at 8. What's going on here? 100 minus x squared is greater than or equal to 0. So negative x squared needs to be greater than or equal to -100. Careful here, x squared better be less than or equal to +100 if we divide both sides by negative. So x needs to lie between what numbers in order for its square not to be greater than 100?
It needs to lie between
10 and -10. I'll just take a number. If it's as absolute value less than or equal to 10, when we square it, its square will be less than or equal to 100.
It can be equal to 10 though?
Yes, since it's in the numerator, we take it. We square the 10, subtract 100, get 0, take the square root of 0, but we don't have to divide by the 0, so that's okay. So as far as the domain of this function goes, I just want to get the domain clear in my mind and maybe everybody's mind, and then we'll look and see where the function is continuous. -10 to +10, but x has to be greater than or equal to -1, so that cuts into the numbers that are between -10 and -1. It cuts them off basically. So we're down to -1 to +10, and then we have to kick out the 8. So it looks like the domain is going to be -1 to +8 union 8 to +10. And I believe it is going to be continuous. I don't think is there a vertical asymptote at -1? What's going on at -1? Well, -1's in the domain. I wouldn't think anything troublesome would happen there. The numerator, nothing awful there. -1 plus 1 is 0 squared is 0, 0. 3 minus that is 3. So it looks like it's fine. It looks like the limit exists. There's going to be a point there at -1. Likewise at 10 is okay. 10 looks like an x-intercept. That seems like that's going to be fine. But what about at 8? As x gets really close to 8, the denominator gets really close to 0, and the numerator does not get really close to 0. The numerator gets close to whatever 100 minus 8 squared is. 36. So the square root of 36. So the numerator gets close to 6. So this is going to be a vertical asymptote. H has a vertical asymptote at x equals 8. So not only are we saying this is the domain of this function, this is the set of values where this function is continuous. It's continuous on -1 to 8. It's continuous on 8 to 10. We can include the -1, include the 10, obviously not the 8 in either case because that's a discontinuity. And there's a vertical asymptote at x equals 8. Once you get the idea with 11, it turns out to be not a difficult problem at all. We just need to think about what's going on in order to make this happen. I think in the homework I introduced an additional variable which limited the possibilities. I think there are a lot of possibilities on values of a and b, a lot of ordered pairs, a and b, that would make this a continuous function. It's piecewise defined, and we're going to think of it as a function of x. There's some unknown constants a and b. I like to establish a relationship between a and b that will guarantee that this is a continuous function. Different values of a and b would give us different continuous functions, so I'm not just talking about one function. It's kind of a function whose definition depends on the values of a and b, but we'd like to choose it in such a way that it's a continuous function at 1 as well as everywhere else. So it is a polynomial, x squared plus 5ax, for all values less than or, well, let's say less than 1, also equal to 1, but in particular less than 1. And it's a polynomial. A linear expression defines it, ax plus b, at all values greater than 1. So since it's equal to a polynomial, on each of those open intervals, it's going to be continuous everywhere less than 1 and everywhere greater than 1. The big question would be, what happens at 1? Where the two pieces meet, are they going to meet at a common point, or are they going to miss each other? And we want to figure out a and b in such a way that they meet rather than missing each other. So what we need is this. We need the limit of f of x as x approaches 1 from the left to equal the limit of f of x as x approaches 1 from the right. I'm pretty sure both limits are going to exist because it's a polynomial either way. There's not a concern with vertical asymptote or any kind of bizarre behavior, regardless of how we define how we choose a and b. So the limits are going to exist. We just need them to equal each other. Now let's see how we would evaluate these limits. If x is a little less than 1, approaching 1 from the left, x is going to be a little less than 1. We define the function using this expression. If x is 0.5 or 0.8 or 0.9, we would use that expression to define the function. So we would substitute into that expression. So to evaluate the limit as x approaches 1 from the left, we would say this is the limit as x approaches 1 from the left of the expression x squared plus 5ax. Now, if we didn't specify that x approaches 1 from the left, I wouldn't be able to indicate it's that quadratic expression. I just wouldn't know. If x is a little more than 1, and we're going to evaluate this function, we would use that expression because that defines the function if x is greater than 1. So this would be the limit of the expression ax plus b as x approaches 1 from the right. Now, since these are polynomial expressions, we can evaluate each limit by direct substitution. We can take the 1 and substitute it for x, and it will, in each case, give us an expression in the variables or yet to be determined constants, a and b. So it's going to be it's going to be 1 squared plus 5a times 1 for that limit, and it's going to be a times 1 plus b for that limit. And we're not going to be able to single out a particular value of A or particular value of B because we have two unknowns, but just the one equation. There's no other constraint on this. So just simplify. 1 plus 5A equals A plus B. And whichever might be easier, solve for A in terms of B or solve for B in terms of A. I'm thinking, since we have B kind of out there almost by itself, it would be easier to solve for B in terms of A. So I'm going to subtract A from both sides to get 1 plus 4A equals B. And so there we go. B equals 4A plus 1. How about that? Now the function is defined at 1, and it's going to be defined. It's going to be defined to be the value of this limit as x approaches 1 from the left. So as long as I ensure that that's equal to the limit of f of x as x approaches 1 from the right, it's going to be continuous. So I need both of the one-sided limits to exist. I need them to agree, and I need the function to be defined to be this at 1. But for any choice of a and b, f of 1 is defined, and it's defined to be 1 squared plus 5a times 1. So it's going to equal this limit. If I didn't have the or equal to bar, it would be undefined at 1. And there would be no way to choose A and B to make it continuous, because even if we caused the limits to define the limits so that they were equal and the pieces of the graph met, there would still be that hole. So I have to have the or equal to bar in order for it truly to be continuous. I don't know. How does this answer feel? B equals 4A plus 1. I don't know. Is that the least bit unsatisfying? I'm going to... Okay, so here is basically our piecewise function. That's how I defined these objects, not too many objects there. We've got f of x equals x squared plus 5ax if x is less than or equal to 1, and ax plus b if x is greater than 1. And for different values of a and b, this is a different function. The graphs look different. We just want to choose a and b so that they satisfy the equation b equals 4a plus 1. So how about if we start with a equals 0? If a equals 0, what would b be? B equals 1. 4 times 0 plus 1 is 1. So how about a equals 0, b equals 1? What's this going to look like? A equals 0. Okay, so what function does that give us? 0x plus b. And if b equals 1, are the pieces going to meet? Yes, there we go. So a equals 0, b equals 1, the pieces meet, and this particular function is continuous. We want a different function, but choosing a and b in such a way that it's continuous. What if a equals 1? If a equals 1, what would b have to be in order to make it continuous? 5. 4 times 1 is 4 plus 1 is 5, so b needs to be 5. Whoops. Come on. Should bring the mouse. There we go. B equals 5. That makes it continuous. And maybe one more. What if a is -3? There we go. A is -3. What would b have to be in order for this function to be continuous? Negative how much? 11. -11. Let's see if I can go that far to the left. Negative... There we go. -11. And so the pieces come together and meet there. So it's... I give it the name f. F really should be kind of qualified, maybe f with a little double subscript of a and b, because the function itself depends on the values we choose for a and b. But if we choose the right values so that there's that relationship between them, then it will produce a function that's continuous at 1 and, of course, continuous everywhere else. the theorem here, there's a lot of possibilities here as far as what sorts of limits we could be talking about. It just, rather than having to write this half a dozen times, we just say take this expression lim and let it denote any one of these possibilities. Maybe a two-sided limit, maybe a one-sided limit, maybe a limit at infinity. If the limit of the function g of x equals L for any one of these types of limits, and the function f is continuous at L, then the limit of f of g of x is equal to what we get when we evaluate the function f at L. Now, one other step I think could be thrown in there, and I've actually included it here. That's good. The limit of the composition of continuous functions, basically, if I say the limit of g of x, if x is approaching c, then we're actually saying that g is continuous at c. So one special case of this would be g is continuous as well as f. So the limit of a composition of continuous functions is a continuous function. So this equals f of the limit. Basically, you can pass the function f through the limit when the function f is continuous and the limit of g of x exists. This will be useful for us. There's an important example involving exponential functions, defining factors, taking the derivative exponential function where we'll want to pass the limit through the function through the limit when we calculate the limit. Discuss the continuity of each function. Well, basically, we just want to observe that we're dealing with two functions that are both continuous on their entire domains, and we're taking the composition of those functions. So if we look at 12 here, and we have the function, let's see, I almost wish I'd called this function h. I called that one h. Let me call this one maybe capital H. Capital H. Because if I let g of x equal 2x minus 3, that's a linear function, it's a polynomial, it's continuous everywhere. And let f of x be the function sine x, we have not proven, but we have stated and believed that the sine function, by what we know of it, is continuous everywhere. So big H of x then would be the composition f of g of x, and according to the theorem above, then it is, since f and g are both continuous everywhere, likewise is the composition of these continuous functions. Little h of x, cosine x, if we let little g of x equal the inside function, cosine x is defined everywhere, also continuous everywhere. F of x is the absolute value function. Now, what we know about the absolute value function is graph is v-shaped, and the two pieces of the graph intersect at the origin. It's basically two linear functions, f of x equals x and f of x equals negative x, pieced together in such a way that they meet at the origin. So it's continuous certainly everywhere except 0, but it's also continuous at 0. So absolute value function is continuous everywhere. So little h of x equals f of g of x, and as a consequence, it too is continuous everywhere. So we just observe that each of the component functions is continuous everywhere, so the composition of them is also continuous everywhere. One important property of continuous functions is that if they're defined on a closed interval, then if we evaluate the function at the two endpoints, the function actually has to take on every value in between the values where they're defined at the endpoints. We'll look at a special case of this in finding zeros, but actually, let me just look at the intermediate value theorem itself. So picture f is continuous on the closed interval AB, and k is any number between f of A and f of B. So let's just imagine f of A is maybe right there, and f of B is maybe right there. So we take a little snapshot, and really all that we can see is those 2 points. But we know the values, f of A and f of B. K is any number in between. Maybe k is right there. What the intermediate value theorem says is that if this is a continuous function on the closed interval, there's some number, maybe a bunch of numbers, but at least one in between A and B, number C perhaps, such that f of C equals k. Now it doesn't give us a way to find it, so I shouldn't speculate that it would be right there. It could be really close to A or really close to B, or halfway in between. But there's some number in C, some number in this closed interval, f of C, f of that number equals k. So if it's not continuous, then pretty clearly it doesn't have to happen. If we have a nice little jump in the graph, or actually I could have brought it all the way down and had a hole in the graph right there with the y-coordinate of k, and defined the function to be something else right there. It's still defined on the closed interval, but if it's not continuous, then this doesn't have to happen. But if it is, then let's see, let's draw a horizontal line here, somewhere in between. Can we connect the dots without crossing the purple line? If the function is going to be continuous. That's not allowed, of course. At some point, we've got to cross that line, and right there, that's the C, where f of C equals k. It's what we call an existence theorem. It tells us that C exists. It doesn't give us a mechanism for finding it. We kind of have to figure that out on our own, but sometimes it's helpful to know that a solution exists. That way, maybe it's worth our while to go looking for it. Until we're convinced that it exists, we don't have as much motivation to spend extra time and resources and so on trying to hunt it down. The example that we want to look at for the intermediate value theorem has to do with the existence of zeros on a closed interval. If we know the values of the function at the endpoints. So we have a function, and I really hate to look at the graph of this. I want to use the graphing calculator because I'm lazy, and I don't want to. Maybe I'm not lazy, but at this moment I'm feeling it, and maybe I don't want to take the time to evaluate the function at 2, at 3, at 4, and at 5, which is what it's going to require of me. So maybe I'm not really lazy, but I just want to be as efficient as possible. And so I'm not going to use the graph. I'm going to restrain myself from picking at the graph, but just use the table feature on the calculator. So let's see, like that. So y equals, probably in the time I can punch this in, several of you can easily figure out what the value of this function is at 3, 4, 5, and 2. Because I'm still getting accustomed to the new operating system. Minus 6x squared plus 3x plus 16. All right, I don't want to peek at the graph. I just want to press second followed by window to make sure that my table setup is okay. Second button, then the window button. I want to make sure if I'm looking at the table, the independent variable is set to ask. If the independent variable is set to ask, then it doesn't matter. Well, it doesn't matter what the table start or the increment are. That's only if it's set to auto. So that's good. I want the dependent on auto. So I'm going to press second and then table. And there are a lot of values that we needed some time ago. Let's go with 2 and 3. So it says that f of 2 equals 6 and f of 3 equals -2. Now this is a polynomial function, So it's continuous everywhere. In particular, it's continuous on this closed interval from 2 to 3. What does the intermediate value theorem tell us about the existence of a 0 on this interval? 1 has to exist. 0 is between 6 and negative 2. 6 is positive, negative 2 is negative, 0 is in between. So there's got to be some number between 2 and 3 where a 0 exists. So the intermediate value theorem guarantees the existence of at least 1 0 on, and I can say the open interval, but we know the 0 does not happen at 2 and at 3 because it's not equal to 0 there. So I guess I will say the open interval, 2, 3. Has to happen in between. It doesn't happen at the endpoints. So let's try evaluating the function at 4. F of 4 equals negative 4, and f of 5 equals 6. Need to copy and paste messy handwriting, but would it be appropriate in this case? What do you think? I think so. Had to edit it just a bit. The intermediate value theorem also guarantees the existence of at least 1 0 on the open interval for 5. There's not a 0 at 4, there's not a 0 at 5, but a 0 is between negative 4 and 6. And because it's a continuous function on the closed interval 4 to 5, f takes on every value between negative 4 and 6, so in particular it takes on the value 0. What about the interval from 3 to 4? F of 3, already done that, that's negative 2. F of 4 equals negative 4. What does the intermediate value theorem have to tell us about the existence of zeros on this interval? It does not guarantee the existence of a 0 on this interval. It doesn't tell us there's not one. That's absolutely right. There could be, as far as we know, based on the information that we have, there could be a 0. It could equal negative 2 and negative 4 here, and then just kind of come up and intersect the x-axis several times if it really needed to. We know a little bit more about the polynomial, so I guess there's only so many times this third-degree polynomial can do that sort of thing. But the intermediate value theorem gives no information about the existence of zeros on the open interval from 3 to 4. Now, 2 to 5, in some ways we have to say it depends, because if at this point we want to know, are there zeros on the interval 2, 5? Well, we've already used the intermediate value theorem to conclude there is a 0 between 2 and 3. And there's also a 0 between 4 and 5, and those are actually two different zeros. So from our use of the intermediate value theorem on these two little subintervals, we know that there are at least two distinct zeros on the interval from 2 to 5. However, if I apply the intermediate value theorem just to the interval 2, 5 without any prior information, what does it tell me? F of 2 equals 6, and F of 5 equals 6. In fact, with the same value of both endpoints, the intermediate value theorem doesn't tell us anything about any value that this function may take on in this interval, except it's equal to 6 at each of the endpoints. That's it. Nothing else. So I could almost say it gives no information at all, but I will say this. Without any prior knowledge, the intermediate value theorem gives no information about the existence of zeros on the interval 2 to 5. That's not what I wanted to do. I didn't want to take a picture of it. I wanted to select it. That's fine. All right. Good enough. A lengthy section indeed. I'm not going to place the emphasis on the epsilons and deltas for these infinite limits that I did on just the limit as x approaches a number equals a number, but I at least want to give an idea of how one would do such a thing. So let's look at the official definition and see if I can put a picture with it. Zoom out. Out. There we go. Just a bit. The idea here is this. Let f of x be defined for all x in some open interval containing c, except that f need not be defined and often is not defined for the functions that we typically consider at c itself. If we're going to be able to write the limit of f of x as x approaches c actually equals infinity, then, well, what might the picture look like? Somehow the graph is becoming arbitrarily high. The function value is arbitrarily large, becoming arbitrarily large in this interval, and it's going up, up, up on both sides. So something maybe like this, and then something maybe like this is the typical picture that we think about if f of x approaches infinity as x approaches c. So what does this mean? Giving any positive number m, well, let's see, positive number m, let's go with m right there. So horizontal line, or an attempt at a horizontal line. There we go. For any horizontal line m, no matter how high we might draw it, there exists a delta. Let's see, you don't want to go too far to the left or too far to the right. This is going to be, that's too far to the right. Let's bring it in a little bit. And since I had to bring that one in, I want it to be balanced on each side of it. That's exactly the same distance on both sides. So, well, close. C plus delta, C minus delta. And look at the vertical lines associated with this. Maybe. I had to fudge it just a little bit. There exists a delta greater than 0 such that f of x is greater than m for any x in that interval except possibly at c where it's undefined. So I just want to make sure that as long as I'm close enough to c, that if I evaluate the function anywhere in there, it's going to hit above that horizontal line. If I move the horizontal line up higher, then I might have to shrink the interval around c, get closer and closer to c, so that it's going to be higher still. So as a rule, the higher the m goes, the smaller delta has to be in order to make this happen. Now, we can do a similar definition, turn the graph upside down, and talk about what it means for the limit of f of x as x approaches c to equal negative infinity. Becoming arbitrarily large in the negative direction, unbounded below basically, and we could write a similar definition there. Now, try to be as clear as possible. To say that the limit equals infinity is not to say that the limit exists. Our definition of what it means for a limit to exist, it has to equal a real number. It has to equal L, where L is positive or negative or 0, but not go off to infinity. Writing infinity is just being a little bit more specific than DNE. Technically, this limit does not exist. We write infinity to describe the manner in which it fails to exist. So it's a little more specific than DNE. If I give you this limit on the test and you say DNE, while true, is not the answer I'm looking for. If you can be as specific as positive infinity or negative infinity, you want to go ahead and do so. Now, what we'll see is that for those vertical asymptotes where the graph goes up to positive infinity from one direction and down to negative infinity from the other direction, and the two one-sided limits don't, well, what I just said, don't go to the same infinity, then really all we can say is DNE. If we're talking about the two-sided limit, sometimes we'll break it down and talk about the two one-sided limits. In that case, all we can say is all we can say, but here we can actually say positive infinity. Example 1, let's be as specific as possible here. We are talking about the one-sided limit here for the first couple of them. X approaches 3 just from the right. We could draw the graph, and I think it would become clear, but hopefully it's clear enough without the graph. If we were to use a table of values and choose X equal to 3.1, 3.01, 3.001, all values slightly greater than 3, what would we observe about the Y values? They get big. 3.1, 3.01, 3.001. We're looking at, I want to say 10 for this one. 3.1 minus 3 is 0.1. And 1 divided by 0.1 is 10. For this one, I want to say 100. 3.01 minus 3 is 0.01, and 1 divided by 0.01 is 100. And for this one, I want to say 1,000. 3.001 minus 3 is 0.001. 1 divided by that is 1,000. So we get closer to 3. The numbers grow larger, 10, 100, 1,000. And we don't have to consider what's going on the other side of 3, at least not until we get to the B part. So this equals positive infinity. It's just the one-sided limit. The other side is doing something else. If we say X and 1 over X minus 3, 2.9, 2.99, 2.999, approaching 3 from the left. Is this negative 10? And negative 100? And negative 1,000? Get a number that's just a little less than 3. Subtract 3, you get a number that's a little less than 0. If you take 1 and divide it by a number that's a little less than 0, you get a great big negative number. So this one equals negative infinity. Of course, neither limit exists, but we can be as specific as positive infinity or negative infinity in the manner in which they fail to exist. However, for the two-sided limit, we've basically explored all that needs to be explored about this. Since the two infinities don't agree with each other, it's going, what, from the right is going up, from the left is going down. I'd like to say plus or minus infinity, but really that's not appropriate. So the best we can do is say DNE. And that's a little unsatisfying. but that's what we say. What if we square the x minus 3?
It all goes to positive infinity.
It will go to positive infinity because that'll cause it to go up both ways in a little bit more extreme or less extreme fashion. More extreme. If x equals 0.1, that's going to be 100. X equals 3.1. Then it's going to be 100. If x equals 3.01, I guess it'll be 10,000 in that case. So yes, it'll increase in a more extreme manner. Example 2. In the past, when this section has gotten included on the first test, the main limits test, I'll usually put a problem like this on there, where I think the first one, you just plug in the 3. The second one, you factor the numerator and denominator and divide out the x minus 1. And the third one, you do that, and the limit still doesn't exist, but you have to talk about the limit at infinity. So I don't even know if I want to do the first one, but it would be something like this. Whatever that works out to be. This one, since we've kind of been there and done that, check my arithmetic, did I do that right? The last one, though, we can do the same sort of thing. Because it's the same expression that we're dealing with. It's going to be 2 over x minus 4, but the limit as x approaches 4, if x is a little more than 4, we get positive values. So what we can say is the limit as x approaches 4 from the right equals positive infinity, but the limit as x approaches 4 from the left equals negative infinity. So the two-sided limit, the best we can say is it simply does not exist. It's going to positive infinity from one direction, negative infinity from the other direction. So this limit, and maybe put it up there somewhere, does not exist. What did the first one work out to be? Did you want to get that?
-2.
What? -2? -2? All right. Thank you. You feel okay about this one? No? We've been talking about vertical asymptotes. Basically, official definition, probably about as technical as we need to be. If f and g are continuous functions on an open interval containing c, and if f of c is not 0 and g of c is 0, then there exists an open interval containing c such that and there exists an open interval containing c such that g of x is not 0 for all x different from c in the interval. Goodness. Then the graph of the function has a vertical asymptote at x equals c. Just have to be a little bit more careful than with the definition of vertical asymptote than typically we do in college algebra, because if g behaves really, really badly, even if g of x equals 0 and f of x is not equal to 0 at c, there may still not be a vertical asymptote. So we have to additionally ensure that there is a little open interval containing c where, although g of c is 0 right there at c, it stays away from 0 in a little open interval containing that. Kind of on the technical side, I guess the best thing to do would be to give an example where if G could equal C infinitely often, maybe think of the example of sine of 1 over x. Something like that, where there's some kind of bizarre oscillating behavior where G could be 0 infinitely often in a little interval containing C. It's not enough just to say G of C is equal to 0 and F of C does not equal to 0. We have to be a little stronger than that in our requirement for a vertical asymptote to exist. For the functions that we're accustomed to dealing with, though, that's the way it happens. If we look at our expression here, and if we substitute, what? 3 for, is it 3 or negative 3? Well, there are two different numbers that make the denominator 0. But only one of them produces a vertical asymptote. Let's see, f of x equals x minus 3 over x plus 3 times x minus 3. So negative 3 makes the denominator equal 0, but does not make the numerator equal to 0. The numerator is close to, well, is equal to negative 6 at negative 3. So the negative 3 is going to result in a vertical asymptote. X equals negative 3. What happens at positive 3? 0, 0. There is a hole in the graph. There is a hole in the graph at 3, and if we calculate the limit as x approaches 3, we'll see what that is. That would be 1/6 maybe? 1/6. If you divide out the x minus 3's, and then you have the expression 1 over x plus 3, you're letting x get really close to 3, that's going to be really close to 1/6. So that's the hole in the graph, but the vertical asymptote is what we're looking for, and the only vertical asymptote is this. G of x, got a cubic, two candidates for vertical asymptotes, x equals negative 2 and x equals negative 4. We could check and see if either of these numbers makes the numerator 0. And it might be helpful to use synthetic division to do this, because not only do we see are they zeros or not, but it also helps us take a step toward factoring the numerator. So let's go with negative 2, 1, negative 6, negative 1, 30. Bring down the 1, multiply and add, multiply and add, multiply and add. Negative 2 times 1 equals negative 2. Add to get negative 8. Negative 2 times negative 8 equals 16. Add to get 15, and negative 2 times 15 equals negative 30. Sure enough, negative 2 is a 0 of the numerator, and x plus 2 is a factor of the numerator. What's another factor of the numerator? X squared minus 8x plus 15. And that is x minus 5 times x minus 3. Okay. What's the vertical asymptote? It's not x equals negative 2, huh? Because negative 2 makes the numerator, makes the denominator 0, but also makes the numerator 0. So no vertical asymptote there. But x equals negative 4 makes the denominator 0 without making the numerator 0. Makes the numerator something else, but not 0. Because x minus 4 is, x plus 4 is not a factor of the numerator. So that's what we have, x equals negative 4. Now something I feel like I should say about almost kind of like a semi-converse for the theorem we just had. Basically, we've got the functions defined appropriately on little open intervals containing C. F of C is not 0, G of C is 0, and stays away from 0 in a little open interval containing C. That guarantees that we have a vertical asymptote. But what if we don't have that situation? Does it mean that we don't have a vertical asymptote? That is, suppose f of 3 equals 0 and g of 3 equals 0, and we're looking at h of x equals f of x over g of x. Can we conclude that H does not have a vertical asymptote at x equals 3? Be a great time to wonder if it would be an appropriate time for a break. Almost, not quite. Maybe we should take a break and think about this. Let's do. When we look at some of these functions and talk about infinite limits, a lot of times I'll say, okay, well, the denominator is 0, the numerator is not 0 at a particular number, so there's a vertical asymptote. And at other times I'll say, well, they're both 0. In one of the cases where like the x minus 3's will divide out, so maybe the limit exists. Well, I don't just feel like the limit has to exist just because 0, the number, makes both the numerator and the denominator equal to 0. So here's a situation. Can we define a function where f of 3 is equal to 0, g of 3 is equal to 0, f of x over g of x, but maybe it doesn't have, or maybe it does have, a vertical asymptote at x equals 3. So these are the possibilities. P of x, q of x, and r of x. X minus 3 quantity squared over x minus 3. 3 makes the numerator 0, 3 makes the denominator 0. Does it produce a vertical asymptote? If we divide out the x minus 3's, that leaves us with x minus 3. What's that graph going to look like? Y equals x minus 3. Basically, a straight line with a little hole in the graph where 3 would be, x coordinate of 3 would be. So no vertical asymptote there. What about x minus 3 over x minus 3? Divide out the x minus 3's. It's undefined at 3, but it's just 1. So it's a horizontal line with a little hole with an x coordinate of 3. And then what about x minus 3 over x minus 3 quantity squared? Divide out a couple x minus 3's, and we'll still have an x minus 3 in the denominator. So even after completely simplifying, the denominator still goes to 0. So whereas the first two did not have vertical asymptotes, this one will. Because in simplest form, the denominator is still going to 0, and the numerator is not at that point. So let's see, if I'm just looking at 1 over x minus 3, I think 4 probably looks something like this. Vertical asymptote there, something like that. And I believe the graph looks like this, and that. So there will be a vertical asymptote there. So just because the numerator and denominator both go into 0 doesn't mean there's not a vertical asymptote. There may be and there may not be. Properties of infinite limits. Let's say these properties make sense. Suppose that c and L are real numbers and f and g are functions such that the following happens. Limit of f of x as x approaches c equals infinity. And the limit of g of x as x approaches c equals L. So L might be 0 unless it's specified that it's positive or strictly negative. But L is not infinity. So we'd like to be able to say something about the limit of f of x plus g of x as x approaches c. Well, f of x is going to positive infinity, g is going to L. Regardless of how great L might be in the negative direction or the positive direction, if f of x is going to infinity, it's taking g of x with it, and it's going to infinity. So the limit of f of x plus g of x is going to be infinity, regardless of the value of L. So we have that. Now, the limit of the product, if L is positive, if g of x is going to a positive value, and f of x is going to infinity, then regardless of how small L is, or regardless of how close to 0, if f of x is going to if f of x is going to infinity, it's going to take g of x with it. It's going to go to positive infinity. And if g of x is negative, regardless of how close to 0, no matter how small, the product is going to flip the sign. It's going to make it negative. So it's going to take it to negative infinity. Now, if L is 0, I can't conclude, I guess I should make this point, if L equals 0, then the limit of f of x times g of x as x approaches c is an indeterminate form. And then it somehow, in some ways, will boil down to what goes to 0 faster. Does g of x go to 0 faster, or does the reciprocal of f of x go to 0 faster? I'd say, does f of x go to infinity faster than g of x goes to 0, but it's kind of hard to quantify that. So if it's a product and one factor is going to infinity and the other one's going to 0, I can't just call it 0 and I can't just call it infinity. We can think of cases where that it might be infinity, it might be 0, or it might be some finite number in between. So it's an indeterminate form, and we just have to have more information before we evaluate that limit. And then the quotient, g of x over f of x, regardless of whether g of x is going to a positive value of L or negative value of L, or if it's going to 0, if f of x is blowing up and g of x is not, then it's going to drive the value of the fraction toward 0. And we've seen that principle in limits that we've evaluated. Okay, and each of these, I think we can apply the properties above. If we can think what's going on with these trig functions, of course x is approaching pi over 2 from the left. I think a quick graph of the secant function would be helpful to see what's going on here. I never have the graph of the secant function in my mind, but I usually have the graph of the cosine function in my mind, and that's reciprocal of the secant. So a quick sketch of the cosine function, close to pi over 2. Cosine starts at 1, and then goes to 0, and then goes to negative 1, and then back to 0, and then back to positive 1, where these, of course, are pi over 2, pi, 3 pi over 2, and 2 pi. So I can put the pi right there. So cosine does, I should make it dotted or dashed or something like that. Cosine does something like that. Now wherever cosine is 0, it's reciprocal. Secant has a what? Vertical asymptote. So secant has vertical asymptotes there. What's the reciprocal of 1?
1.
1. So when cosine is 1, secant is 1. Now as cosine heads down towards 0, reciprocals of numbers that are headed towards 0 from above are heading toward positive infinity. So that's what secant's doing. And as cosine, let's see, as x comes up here toward pi over 2, through these negative values, tiny, tiny negative values for cosine, I forgot to ask, what's the reciprocal of -1? -1, yeah, so secant of pi is -1. Secant's doing this. There we go. So then you can draw the rest of the secant graph if you want it. We don't need the rest of the secant graph, but that's kind of what's going on. So as x approaches pi over 2 from the left, so we're doing this, pi over 2, oh, wait, that's the right. That's the right. And I erased the x-axis and no telling what else in the process. Put it back. From the left, it's doing this. Secant is going where? Positive infinity. So secant x is going to positive infinity. X is going where? Well, as x goes to pi over 2, where does x go? Pi over 2, yeah. Pi over 2. So x is going to pi over 2. Secant's going to positive infinity. So we can apply this one right here with L positive, and the other one going to positive infinity. So the product is going to be positive infinity. There we go. From the other direction, there we go, should have just done this one. From the right, x is going to pi over 2. Secant is going to negative infinity, down like this. And so we have positive numbers times arbitrarily large negative numbers. And that product is going to be larger and larger negative numbers, so negative infinity. And the C part, it illustrates, I think, C part is intended to illustrate this first one here, but it seems fairly obvious. And I think it is fairly obvious once we see what cosecant is doing. Cosecant and sine are reciprocals of each other, yes? No? So sine, as x goes to 0, sine of 0 is what? Sine of 0 is 0. Yeah? So that sine is going to 0. Cosecant, now if x is a little bit more than 0, just a quick peek at the sine function. If x is a little more than 0, is sine, over here, right here, is sine positive or negative? It's positive, yeah. So cosecant is positive, so evidently cosecant is going up like that. That's what cosecant's doing as x approaches 0. So let's get rid of the sign. So positive infinity. So cosecant is going to positive infinity, sine is going to 0, and their sum very easily is going to positive infinity. There's just no worry at all if there could possibly be anything else. Okay. The M delta definition. Our textbook doesn't emphasize it all that much, and I'm certainly not going to ask you to do it on the test. If you love this sort of thing, then definitely indulge yourself in example 5. On the other hand, if its effect on you is similar to that of drinking Ipecac, then don't worry about it, because it's not going to be on the test. All right. Goodness gracious. Most important thing we talk about all semester long, and it's got to happen at the last 15 minutes of class. It's got to happen sometime. Let's talk about the average rate of change. Let's talk about the definition of the tangent line to a function, the slope of the tangent line, and then we'll have more to say about the derivative next time. When you printed your notes, did they look at all like this? Is that what they look like?